Welcome to lecture 18 on the proof complexity as a computational lens course. We are in the middle of a lower bound on PCR monomial space, proving that monomial space is lower bounded by the square root of resolution width, basically. Just a quick recap, what did we do last time? So last time as a warm-up, we proved the total space lower bound. We said that if the width of refuting a formula in resolution is W, strictly larger than W, then in fact that tells us that the total space of refuting F is W squared, except dividing by a constant factor 8. We stated this as holding for W just being at least the initial width of the formula. The proof we gave actually doesn't quite work, it seems. I haven't had time to think about whether it could be fixed. One easy way to make it true, and this is what we mostly care about anyway, let's just insist that the width that we're proving the lower bound for is at least 4 times the initial width of the formula. Then everything should be okay. So to be on the safe side, let me state that if the width is at least 4 times the initial width, then the total space is at least width squared over 8. And just to see how did we get this? Well, we had a more specific theorem which came from Galesi, Kołodziejczyk, and Thapen, which said that if F is a k-CNF formula and R and S are any parameters, R greater or equal K, such that there is a configuration style resolution refutation pi of F, such that in any configuration there are at most S clauses that have large width strictly larger than R. If there exists such a refutation, then this implies that the width must be upper bounded by 2R plus S. So just to note that we do need this condition on R, and one simple counterexample otherwise is just consider the CNF formula consisting of one very wide clause, x1 or x2 or all the way up to xn, and then just conjunction with unit clauses fixing all of these literals to false. It's not hard to see that this formula has a refutation where you just peel off the variables from the wide clause one by one. So we will have at any time, at most 2 clauses of width strictly larger than 1. But of course, this does not imply that the width of refuting this formula is 4. I'm not sure whether we need the factor 4 here or whether we could work a little bit harder, but at least the proof we did yesterday kind of assumed that we had a factor 4 slide there. So let's just leave it at that. That was what we proved yesterday. Then we continued to develop the techniques that were implicitly used in that proof, and this led us to the notion of forcing. And forcing is relative to families of assignments. What kind of families of assignments? In particular, we're interested in a memory W defendant strategy, which we know exists if the resolution width is at least W. In fact, resolution width W corresponds to memory W plus 1 defendant strategies, but we won't obsess about this additive one today. So a defendant strategy is simply a way guaranteeing that the defendant can play the prosecutor defendant game forever. So in particular, you never need to remember more than W variables. If you shrink any partial assignment, you're still in the family. If you're not at the limit, if your current assignment domain size, which I just denote by the size of alpha, is strictly smaller than W, then you can extend to any variable x while staying inside the family of assignment. And any assignment in the whole family makes sure to never falsify an axiom clause in the formula that the defendant strategy is for. Note that this doesn't mean that alpha satisfies C. Alpha might not have an opinion, but at least it does not falsify C. It's not the case. It's never the case that alpha will set all the different literals in this clause and will set all of them to false. That will never happen. Okay, so for today, F will always be a k-CNF formula. Curly A will always be a memory W dependent strategy in this sense. I will erase these definitions soon. And then with fixing such a memory W dependent strategy, we can now recall what it means to force. Alpha forces some monomial M to 0. And we had this notation, some kind of V dash with double vertical lines. Forces M to 0 if it honestly picks out some literal in the monomial and sets it to 0, so that the monomial vanishes. So that part is standard, it's a classical assignment. Alpha forces M to 1 if there is no way of extending alpha while staying inside the family so that M is falsified. So if no extension beta of alpha falsifies M, or sorry, falsifies M sets, I should say to be precise today because 0 is usually true, no extension beta of alpha sets the monomial M to 0. If that's the case, then no extension beta of alpha sets the monomial M to 0, then we say that alpha forces the monomial to 1. For all practical purposes, we can treat it as being assigned 1 because no extension inside the family of assignments that we're looking at will ever set it to 0. And then this is extended to polynomials in the natural way. We say that a polynomial is forced to value C if the monomials in the polynomials are forced to values bi, and then when you take the sum of these bits bi's with the coefficients in the polynomial, you get C. And then we say that alpha forces a configuration fat M to true if it forces all polynomials in the configuration to 0. If it forces all the monomials represented in the configuration to some value, and it forces some polynomial to non-zero, then we say that it forces not the configuration, which we should think of as falsifying the configuration. And I mentioned last lecture that, in fact, the lower bound that we're doing holds not only for PCR, but the much more abstract so-called functional monomial calculus framework, where we don't care about the polynomials. Any configuration is just a Boolean function on monomials, and the space is just how many monomials do I need to pick to realize this Boolean function. I will not stress this aspect again today. We'll just basically, let's talk today about polynomials, but everything we do will generalize to this very much more general setting. Okay? And this forcing is what will allow us now to prove that PCR monomial space is greater or equal square root of resolution width, except for some constant factors that we will talk about when we get to the theorem statement. Okay, so good. So let us now recap what we did. What did we prove about forcing? So forcing is not the same as truth value assignments. Weird things can happen. In particular, very weird things can happen when you get close to the size boundary of the family. So basically, we proved the number of lemmas saying that as long as you're far enough away from the size boundary of the family curly A, it's kind of a truth value assignment. Okay, what did we mean by this? First, we made the observation that it can never be the case that you can force a configuration to both true and false. Alpha could have no opinion about the truth value of the configuration, but it can never ever force a configuration to both true and false. And the reason for this is alpha can never, just by definition of forcing, you can never force a monomial to both 0 and 1. And then and that means that whenever you force a polynomial, you can only force it to a single value. You can never force something to two distinct values, and then you just sort of compose and reach the natural conclusion that hence, for any configuration, you can only force it to either true or false, but not both. Okay? Then we said, what if alpha doesn't force the value of a configuration? Well, then we said that if alpha is in the strategy, and if I have any monomials, Note that here I don't care about the size of alpha. Alpha could be like super large, but as long as alpha is in the strategy, then throw at me any monomials, and then there does exist a beta in A that extends alpha and forces all of these monomials, and beta is not too large at most sizes. But note that even if alpha is of maximal size, this lemma is still true. Okay, so by extending alpha by at most S literals, we can always force any collection of S monomials. That we proved. And then we said that, okay, if we're just below, remember that the strategy curly A has size W. If we make sure to stay strictly below that size, then in fact forcing is consistent with some truth value somewhere. If alpha is strictly smaller than W and forces a bunch of monomials to values, then there is an alpha star, not necessarily in the family now. This is like a total truth value assignment that actually honestly sets all these monomials to these values. And alpha star is one of the few assignments you will see on the board today. This is not inside the family. Like any alphas and betas, I'll try to remember to write it out, but we're usually operating only inside the family of assignments curly A. But here lemma 10 says that if you're operating inside curly A and you're not at the size boundary, then forcing can't be arbitrarily weird. There is always a total truth value assignment that is consistent with the values being forced. And this now allowed us to say the following. Suppose that I say I know more about my alpha. Alpha is not only smaller than W, it's actually smaller than W minus K, where K is the width of the maximum width of an axiom clause in the formula, and also let's say that K is strictly larger than 2, because proving lower bounds for one CNF formulas is not really interesting anyway. If I know that alpha is smaller than W minus K, then it cannot be the case for consecutive configurations in a derivation from F, MT minus 1 and MT. It can't be that alpha changes its opinion that MT minus 1 is forced to true, but MT is forced to false. That cannot happen. Okay, and that's pretty much where we left off yesterday. Questions about this so far? Like it's all crystal clear. So let me stress again that I don't know about you, but when I prepared the first few times I read this GKT paper, and as I prepared these lectures, this forcing notion is a little bit counterintuitive. So if you're anything like me, you will be a little bit confused. But it's really all we're going to do now. We're going to do utter trivialities. Except these utter trivialities will lead to a super strong proof complexity lower bound. This is the amazing part. This is why I think this paper is so fascinating. Like it's out of thin air, you suddenly get this extremely strong statement that for some weird reason, monomial space is greater or equal square root resolution. So in order for us to understand this, you can help me by whenever I'm making a claim and it's not blindingly obvious, just point out that, hey, would you mind pointing out why this is blindingly obvious? And I'll try to point out why it is blindingly obvious. We're just going to play with this forcing notion. Again, recall that forcing to 0 sort of honestly means setting things to 0. Forcing to 1 just means that there is no way I could extend and force to 0. Okay, and we're just going to play with this notion over and over again. And then we're crucially going to use lemma 10 that says that as long as we're not at the boundary, we are consistent with some truth value assignment. And as long as we're smaller than W minus K, we can sort of argue by induction over the PCR derivation. Okay, and then we know that we've done these kind of inductive arguments before, that, okay, assume that we have a refutation in too small space, and we use inductive reasoning to find an alpha that somehow satisfies every single truth value assignment. What we're going to do now is we're not going to do a proof by forward induction over the derivation. We're actually going to do kind of induction from both sides and meet in the middle. And we're going to find in the end an alpha that actually satisfies MT minus 1, but violates MT. And then we're going to conclude that that is impossible. And therefore, somehow this refutation doesn't exist, and then by contradiction we get the lower bound bracket. That's what's going to happen. Okay. So what we're going to prove, let me actually write it. Let me actually clear it over here, maybe. Let's see. Board technique will be a crucial aspect today also. Let's see if I can get it to work. So the theorem we're going to prove today by Galesi, Kołodziejczyk, and Thapen, journal version from last year, is the following, that if the monomial space, okay, maybe again, F is always a k-CNF formula, but since it's the main theorem of the lecture, let's write it down. If the monomial space in PCR of refuting F is less equal S, then this implies that the width of refuting F in resolution cannot be too large. We are going to prove it cannot be more than 2 times S, 2 times S plus 1 plus K, which is the width of the formula. Okay. Now, if you really want to squeeze the juice out of the proof we're going to do, then in fact, we can improve this just by more careful counting. The proof we do will bring this down to 2 times S squared plus K, so saving an additive S. And this will still work for the functional monomial calculus. This proof that I'm going to do now, I'm stating it for PCR, but in fact it holds for a stronger model. Even in this stronger model, you can get this down to 2S squared. And if you are really going to use that we're in PCR, and you calculate even more carefully, then you can get a better bound S squared minus S plus K. So getting rid of the factor 2 and also subtracting S. But all of this it's essentially all of these results come from the same proof. And if you just do the proof and understand it, this is the first bound you get. And then you start counting more carefully. And then you improve. Okay. So we're not, and in particular to go from here to here, the one thing in functional monomial calculus, you have no idea which monomials you're using in each configuration. Remember, this was an implicational system where the monomials at time t minus 1 might be completely unrelated to the monomials I have at time t. All I know is that the Boolean function over this set of monomials implies this other Boolean function over this other set of monomials. In polynomial calculus, we actually know that the monomial set pretty much stays the same, right? So that is how you get from here to here. And how to get from here to here, from what we do today to the better bound without the additive S, is just by more careful counting. But I think we're gonna suffer enough by just doing the lower one on that. And again, throughout, so what our assumption now is that F is a k-CNF formula, and I'm also going to assume that pi is a refutation of F in space S without loss of generality. We're actually going to assume that K is at least 3. The reason for this is that if K is at most 2, then you can do everything in constant control space. So it's not so interesting. So it's kind of that loosely. What we're going to prove is is vacuously true. Or rather, I mean, if, the way I should say, if k is at most 2, then the width is at most 2. So then the width is in fact smaller than k, so there's nothing to prove. That's the way I should have said. Sorry. And we're fixing A, curly A, to be a memory W different strategy. And it's going to be, since this is the bound that we're shooting for, we're going to set W to be 2s s plus 1 plus k. In fact, if this is the bound we're shooting for, we could afford adding a plus 1, but it's just going to be annoying to carry this one around. So I'm going to, like, I'm giving up one additive 1 in our lower bounds. Already there, I guess I could have, I actually could have stated a -1 here, but we don't have the energy to do that. Okay, so we're all set. So now, if I have a configuration M, and I have an assignment alpha that is in my family, then let me denote by the zeros of M under alpha is the monomials in M, let me write it that way, such that alpha forces these monomials to 0. And recall that this actually means honestly setting them to 0. Let the non-zeros then be pretty much all other monomials. So basically this will be the monomials in M minus the zeroed out monomials. And let me say that alpha guarantees are non-zeros. I'm writing it here because I'll try to keep this definition on the board. It's going to be a key definition for us. Alpha guarantees are non-zeros in the memory configuration M if for all beta that extend alpha, it holds that the number of non-zeros in M with respect to beta is at least R. So alpha guarantees are non-zeros in M if I know that however I enlarge alpha while staying inside the strategy, there are at least R monomials that will not be set to 0. And now a piece of notation. Let me write pi in the interval from L to R. That is just the configurations from ML all the way up to MR. Okay, it's like a sub. It's not a sub-derivation really, it's just a subsequence of configurations. And let's say that alpha guarantees are non-zeros in this whole interval, pi from L to R, if alpha guarantees are non-zeros for MT, for every t in the interval from L. Okay, nothing strange happening except why are we doing this? We'll get to it. But I'm just saying that, like, if during some interval I know that with respect to alpha for all of these I have at least R non-zero monomials, then I just say that alpha guarantees R non-zeros throughout this interval. Are we happy with this? except again the question why, but let's see. The answer to this question we have at this point is maybe because it works. Okay, here's an obvious observation, but maybe it's good to write it down. If alpha guarantees are non-zeros for a configuration or in an interval, and if beta extends alpha, while obviously staying inside the family, as we'll always do today, then it's kind of clear that beta also guarantees are non-zeros. This is just by definition, because guarantees is already looking at all extensions. Okay, so now we know, because why do we obsess about this? Well, because we already know from last lecture that what we're going to do, we're going to extend these assignments step by step, and then it's good to know that all the notions we have behave nicely under extension. Okay. So now, are we happy with the notion of forcing? Do we know it? Because now I'm just thinking that now is maybe the time when I'll get rid of it. Because to replace it with a key lemma, continuing the numbering from last time, this is lemma 13. And lemma 13 says the following. Suppose two things. Suppose that the number of non-zeros in M with respect to alpha is R. And suppose also that alpha guarantees are non-zeros. Guarantees are non-zeros. Then alpha forces M to some value. Okay, what does it say? If I have a lower bound, or if I have if I actually have a bound R on the non-zeros, and I know that alpha guarantees these many non-zeros, then alpha in fact forces the value of M. I don't know if it forces it to true or false, but it has an opinion. Okay, and why do we care about this? Again, because we're going to go over our derivation, and the problem we're going to have is to find alphas that force things. Before we were struggling to find alphas that actually honestly satisfied assignments. Now we're going to find alphas that force, so alpha that satisfy the configurations. Before. Today we're trying to find alpha that forces configurations. And this tells us that if I can get a handle on the number of non-zeros, then that allows me to force. Okay. Are we happy with the prosecutor-defendant game strategy kind of thingy? I'll try to remind you what properties I use from this. Okay. So let's see, why is lemma 13 true? Well, okay. Let's prove lemma 13. Okay, we know that the non-zero monomials of alpha, there are of them. Let me give them names, M1 up to MR. Alpha forces M to 0 for all other monomials in the configuration, right? because all non-zero monomials are forced to zero by alpha. Okay? But now, if we just stare at the definitions, if alpha guarantees are non-zeros, that means that no extension of alpha will zero out these monomials. So by definition, since alpha guarantees are non-zeros, no beta extending alpha is no beta extending alpha can have that beta forces 1 mi to 0. Because then by definition alpha would not guarantee or non-zero. But that means that by the definition of forcing that I now erased, that means that actually this means that alpha forces all of these monomials m1 up to mi to 1, just by definition of force. Okay, but now then alpha is forcing all of the monomials in the configuration. That means that it will force all the polynomials in the configuration, so it will have an opinion about the truth value of the configuration. It will force the configuration to either true or false. Okay. So next lemma tells us that suppose now that the monomial space of M is at most S. So suppose that the monomial space is at most S, and suppose alpha in A guarantees are non-zero. Then we can find a beta extending alpha, beta in the family, such that beta forces the configuration M to some value, and beta is not too large. It's the size of alpha, at most the size of alpha plus S minus R. Okay, how do we prove this? Well, how did we prove lemma 9? Recall that we proved lemma 9 by just looking at these monomials one by one. And if there was an extension beta of alpha that set M1 to 0, then we just extended alpha with that literally in M1 set to 0. So like for every monomial that was set to 0, we extended beta to get beta with one literal more. And then we were left with the monomials that we could not set to 0 by extending alpha to any beta. And those by definitions were already forced to 1 by alpha. So for those we did not pay. Actually, we paid here in the proof of this lemma, we paid not S, we paid the number of monomials that we could zero out. How many monomials can we zero out here? Well, the space is S, and apparently R of them we can't zero out. So we're zeroing out at most S minus R. Are you happy with this? Okay. So then that's that lemma. Now, let's see if I can also fit lemma 15 on the board. I don't know if this is readable, by the way. I hope so. With same assumptions as in lemma 14, but maybe let me write it out. So the monomial space is at most S. Alpha lives in our family. Suppose there is a gamma extending alpha. Gamma is also in the family. And suppose that for gamma, the number of non-zeros is R. Then there exists a beta between alpha and gamma. Beta is also in the family. Beta has size at most alpha plus S minus R, and the same guarantee with respect to non-zeros as for gamma. The number of non-zeros is R. Okay. So if I have an alpha, I don't know anything about it, but I know that the monomial space is not too large. If there is some gamma that is maybe humongously large, but still in the family, that has R non-zeros, then I can shrink gamma to a beta that has the same number of non-zeros, but has size at most S minus R, where you see again, why S minus R? Well, S is the total number of monomials, and S minus R is the number of monomials I need to zero out. Furthermore, if alpha guarantees R non-zeros, in M, then beta and also gamma, they both force M to, and they force M to the same truth value. So if M is, we're using it if the space is not too large, I have some alpha, I'm able to extend it to some gamma which has R non-zeros, then I'm saying, well, you don't need to pick gamma too large. At most, size alpha plus R plus S minus R to guarantee the same, to have the same number of non-zeros R. And if alpha guarantees R non-zeros, if already alpha guarantees R non-zeros, meaning for any extension we have R non-zeros, then in fact, beta and hence also gamma force M to some truth value, and then it has to be the same truth value. Okay. Let's see if we can write that proof down, and then we're basically almost ready to prove the space for bonds. Okay, so let the monomials in M be M1, M2, up to MS prime. S prime is at most S, because we know that about the space. And we divide them up into the non-zero monomials now with respect to gamma. The non-zero monomials with respect to gamma are M1 up to MR. And the zero monomials with respect to gamma are then MR plus 1 up to MS prime. And for these, we know that there exists an Li in Mi such that gamma sets Li to 0, right? Because being in the 0 monomial set means that gamma is actually honestly zeroing out these monomials. So let's just fix arbitrarily for every monomial one literal that witnesses this. There might be many, there's at least one, fix one. So now beta is just going to be alpha union Li is set to 0 for I in the interval from R plus 1 up to S prime. Okay? I claim that beta clearly has the right size. You agree with me? Beta is a sub-assignment of gamma, and gamma is in the family, so clearly beta is in the family because our family is closed under, it's downward closed. And again, recall that just by definition, well, I mean, since beta, okay, we didn't write down a observation about this also, but if gamma, if beta is a sub-assignment of gamma, then the non-zeros of gamma must be a subset of the non-zeros of beta, just by definition. Okay, because beta is a smaller assignment, so it can zero out more things. So the non-zero set can only grow. So it's clear, I guess what I'm saying is that the non-zero set of beta, just because beta is a sub-assignment of alpha, it must hold that it has more non-zeros than gamma, by definition. But the way we did it, we actually see that by construction, we have eliminated everything except the non-zero monomials in gamma. So we have to have equality. I'm kind of beating around the bush. This is blinding Lobis. I'm just saying it in a bad way. Do you agree with me on this? Okay, yeah. So then I claim that we found a beta of the right size, which had the same number of non-zeros. Okay. Now the furthermore part, suppose that alpha guarantees are non-zeros. So if alpha guarantees are, I cannot write today, if alpha guarantees are non-zeros, then so does beta and gamma. Why? Well, because of observation 12. I mean, the guaranteeing non-zeros is defined with respect to extension. Okay, so if alpha guarantees are non-zeros, then so does beta and gamma. And so what that means, by some lemma that we should have on the board now, by lemma 13, so now we have that beta has R non-zeros and guarantees R non-zeros. Hence, beta forces the configuration, and gamma also forces the configuration. Okay, but now gamma is an extension of beta, and if beta already forces something, then we had this as an observation yesterday. Again, the forcing operation plays well with extensions. It can never be that I force to a value and I extend and now force to some other value. Once I've started forcing, all extensions will force to the same value. You're fine with this? Okay. So then, with it was close call, to be sure, mostly due to the lecture, but I'm claiming we established lemma 15 now. Okay. Okay, fantastic. Because then we're done. I'm going to erase this, and I will now. My board is getting a bit on the small side now, but let's see. So here's the main technical lemma. So with assumptions as before. So let's see. Pi is a space, monomial space S PCR refutation. In fact, functional monomial capitals will be fine, but I just don't have the energy to say this. So monomial space S PCR refutation of the k-CNF formula F k greater or equal to alpha is curly A is a memory W defendant strategy for F. For W, the value we're shooting for, or any W, in fact, that is at least 2 times S plus 1 plus K. Then, for each integer R upper bounded by S, there exists a partial assignment alpha sub R in our family, and a proof interval pi left R, right R, such as the following holds. 3 properties. Alpha R forces the left configuration MR to true, but alpha R forces the rightmost configuration R sub R to false. Okay, and it's kind of clear now that if we can keep inside the family and get these guys to be closer and closer to each other, we should be in excellent shape to force a contradiction, right? Because where do we have it? We see that lemma 11 kind of says, lemma 11 already says that we're not going to be able to shrink this interval to size 1. But of course, this is our goal. Okay, and where is this going to come from? It's sort of a, you know, where are we going? Well, if S is too small and W is too large, what are we saying here? There is a defendant strategy. That is, we're assuming a width lower bound this for the k-CNF formula, and we're assuming the monomial space upper bound that for the formula. And if we push these, if we push the width too large and the space too small at the same time, we're going to run into a contradiction. That is our plan, right? So this says that if the space is sufficiently small, then the refutation with lower bound cannot be arbitrarily large. Okay? And we already see that if we're able to get a contradiction for this value of S and this value of W, then in fact, by the fact that these defendant strategies characterize with, we will have exactly this. This is clear? Okay, excellent. And given our obsession with this guaranteeing non-zeros, you kind of already guessed that alpha R is going to guarantee are non-zeros in the whole interval from L sub r to capital R sub r. Okay, what is this third property that I need? Why did our proof that remember we tried to do a proof yesterday also just by forward induction, and it broke down miserably because the assignments got too large, right? So while doing this, I'll better make sure that alpha r is not too large. What's the lower bound I want? Well, turns out that the magic number is going to be I goes from 0 to r minus 1, s minus I, where the space bound is at. Where you see that at the end of the day, when r is going to hit s, we're looking at some kind of s square-ish bound here. And then we just need to do the math. And we'll do the math in a bit. Okay. This is the technical lemma that we need to prove. I claim that if we get lemma 16, then we're done. And my plan was to prove the theorem using lemma 16 and then try to prove lemma 16. Okay. Okay. So good. I mean, it's clear what we should do. We proved this lemma we proved this theorem by contradiction. Proof of our main theorem by contradiction. What do we mean? Well, fix a refutation in this space. Suppose that this lower bound is false. Well, then there is a defendant strategy with W equal this. In fact, with W equal this plus 1, but I'm not going to use it. I'm just arguing that the plus 1 goes in the right direction. There's definitely a memory 2ss plus 1 plus k defendant strategy. So fix that. Okay. Apply now lemma 16 with r equals s. Okay. So now we get alpha s forcing some m capital L sub s, but let me just write it capital L to true, and alpha s forces m capital R. This is again r sub s, but I don't write that out, to false. Now, we're still not done because we don't know how far apart these are. There might be quite a long interval, but we know that alpha s guarantees s zeros in pi LR. Thank you. I think that will be much better for us. Yes. And now we kind of know, again, where do we have this lemma? We have lemma 13 that is giving us hope. Now we're in a situation where we're in an interval where we're guaranteeing many non-zeros. So if we could just push up these number of non-zero terms to hit the right bound, then we should be in excellent shape, except these are far apart. So we're going to have to do some kind of final induction from L to R, which means we better not be at the limit. Happily, we're not. How large is alpha sub s? Well, at most, this large. So 4 times summing from for I goes from 0 to s minus 1, s minus I, and this will just be 4 times s plus 1 over 2. And by a miracle, this is 2s plus 1, which by another miracle happens to be w minus k. And it so happens that we have some really nice lemmas that say, well, if you have slack k, then you can do nice things. So it's all coming together for us now. Okay. Lemma 13. I mean, note now that we're hitting the space bound. So we actually know we have equality here. I mean, that we cannot have more non-zeros like this. This has to be an exact equality because this is the space bound. I mean, if you're guaranteeing s non-zeros, then in particular it means that the number of monomials is at least s. But by assumption, s is a lower bound on the space. So throughout this interval, we're hitting space exactly s. So we actually know that the number of zeros is exactly s, and we're guaranteeing s zeros. Then lemma 13 says that alpha sub s forces. Okay, let me write. We don't know the truth value yet. Let me just say that alpha sub s actually forces all configurations mt for t in this interval. Then lemma 11 plus induction says that we have a memory W dependent strategy. We have a k-CNF formula. K is greater or equal to 3, so that's fine. Alpha is not too large. Then it cannot force successive configurations to different values. So in fact, for all t in LR, we have now that alpha s forces mt to true. But this is a contradiction. Because alpha s by, we know that, is supposed to force MR to false. So now we have an assignment that forces a configuration to both true and false, but forcing doesn't behave that way. That could never ever happen. So we're done. Questions on this? So now we have our main theorem. We prove now, assuming lemma 16, which we very much have not yet proven, we have shown now that, well, if the monomial space upper bound is S, then there cannot be a 2S times S plus 1 plus K dependent strategy. Which means exactly that the width, the resolution refutation width is upper bounded by 2S times S plus 1 plus K, scaling like S squared. Okay. Meaning, turning it around, that a width lower bound W would give qualitatively a monomial space lower bound square root W except for cont. Okay. Okay, let's prove the lemma. We're going to do it by induction overall. The base case is we need to find an L and an R and an alpha such that alpha forces ML to true, MR to false, alpha guarantees 0 non-zeros throughout the interval, and alpha is, well, ideally is size 0. And indeed, let's pick the empty assignment. We don't have much by way of choice, right? And let's pick L to be 0. Let's pick R to be tau, end of the proof. Guaranteeing 0 non-zeros is a vacuous condition. So this is 2 is okay. The initial configuration is emptiness, which is truth. So it's forced by anything. Falsity is forced to false by anything. And the size conditional. So the base case for the induction is triple. Okay. So we only need to care about the inductive step. Suppose that 1 to 3 hold for alpha R and pi LR RR. So here's a picture. And what I'm going to draw now, let's see, I'm going to cheat a little bit. So on the y-axis, we're going to have the number of guaranteed non-zeros. And since we're in the middle of the inductive argument, we have had something like, first we had the guarantee of 0, I went up to a guarantee of 1, maybe a guarantee of 2, and pretty immediately to a guarantee of 3, and maybe that's where we are right now. See, let me try to stay consistent. 1, 2. Okay, I'm not sure. Something like this. So here is the configuration MLR. Here is the configuration MRR. And we know that, we've found some alpha R here, and before here we had some, alpha R minus 1, and then before that we had some alpha R minus 2, but this is the guy we're thinking about right now. And with respect to this guy, we know that we're guaranteeing this many non-zeros throughout this whole interval. And in fact, let's say that the true picture is something like how many non-zeros do we have? Maybe over time it looks something like this. Right? This is the picture that we have. We're going to start working on this side. And we have two cases. Case 1 is I can find a t prime in this interval that we're working on now. And I can find a beta prime extending alpha r. And beta prime is, as always, we want to stay inside the family. Such that the number of non-zeros in mt prime with respect to beta prime is exactly r. Note that this is like, we're nervous somehow about these points. Like we know that we need to find a subinterval where we can actually raise this bound by 1, right? So these points here are kind of problematic ones. And this case A is identifying one of these points. And let's suppose furthermore that it holds that beta actually forces this configuration MT prime to true. Okay, case A is suppose there is such a T prime on the left-hand side, or suppose otherwise there is no such T prime. Okay? You realize now that, well, if there is no such T prime, then in fact, already alpha R here, I mean, T equals T prime would be a valid choice because definitely we know that there is a beta prime, namely alpha R, that forces MT to true. So T prime equals T would be a valid choice. But if there is no such T, then the only reason that T prime equals T is not valid is that alpha R is in fact already here guaranteeing more zeros. So that's kind of an easy case.
Sorry, when you say T prime is equal to T, you mean T prime is equal to LR?
T prime is equal to LR, thank you, yes. I could pick T prime to LR because I know that alpha R forces MLR to true. So the only thing, the only reason why LR would not be a valid choice for T prime is that this equality about the number of non-zeros doesn't hold, which means it has to be strictly larger. Okay, so let's just deal with this case immediately. If there is no such T prime, then I will build a new alpha prime. I will just let it to be alpha R, and a new left-hand interval limit will just be the same LR. And I'm going to use that at this point, actually, I know that alpha R actually has R plus 1 non-zeros in that case. Okay, but suppose in general there will be such a T. So let's fix it. So case B is case A is like the case where we need to do some work. So we fix a maximal T prime and the corresponding beta prime. Okay. I pick T prime of maximal value satisfying this, such that there exists some beta prime, and let me also fix such a beta prime. Okay. Now I claim that since you can never force a configuration to both true and false, and since forcing behaves nicely with respect to superassignments, we have to have T prime strictly less than RR. Do you agree with me? Because we know that alpha forces the right-hand side configuration to false. So every extension would do the same. So therefore, T prime cannot possibly be the right-hand side. Okay? So this is by condition 1. By condition 2, plus lemma 15, I've now found, now beta prime is my gamma that has number of zeros exactly this. Then I'm saying without loss of generality, I don't need beta prime to be larger than this. So let's just shrink beta prime. I know beta prime is at most alpha R plus S minus R. Okay. Again by 2. Plus lemma 14. You can extend beta prime to an alpha prime in the family such that alpha prime is at most the size of beta prime plus s minus r again, which is at most alpha r plus 2 times sr, s minus r, and alpha prime forces mt prime plus 1. I'm just using that. I know the space bound. I have an alpha. I know that alpha guarantees are non-zeros. Then I just extend it to make it to force this assignment. So, but note that it's important thing now. We were operating at t prime before. Now we're going to t prime plus 1. Okay. And by the calculations we had before, if you think about it, alpha prime is clearly less than w minus k. And that makes, from lemma 11 then, says that the forcing actually has to be true. Because mt prime and mt prime plus 1 are consecutive. Alpha prime is not too large. We did this calculation already when we applied the lemma to prove the theorem, and then we plugged in the maximal r equals s. So the bound clearly holds for smaller r. Okay, so let's see where we are. So basically, we found t prime and okay, the scale is not amazing. Maybe let me draw it this way. We found t prime, and here we had m t prime plus 1. And we have an alpha prime that is not too large, and it forces mt prime plus 1 to true. And let's write down that alpha prime is less than alpha r plus 2 times s minus r. Okay. Now we're ready to work on the right-hand side. Again, we have 2 cases. Case C, there exists a t double prime in L prime. So this is now L prime, right? T. Oh, did I say this? I said A alpha prime to this. I said L prime T prime plus 1. And now I'm looking for a t in the interval from L prime to LR, a t double prime, and a beta double prime extending alpha prime. Beta double prime should obviously be in the family, as always.
It's L prime to RR.
Yes, thank you. So again, we're interested in seeing this picture's not so. Maybe let's suppose it looks now something like this. So again, now I identified, note that we found now the last point. T prime was the last time when I only had R non-zeros and I was still forcing the configuration to true. So now sort of I'm going to scan from the other side and find the last time when I have only R non-zeros. Okay, so where am I? There is a beta double prime in the family such that the number of non-zeros in M T double prime with respect to beta double prime is down on the mid. We know that it's at least R. I'm interested in when it is exactly R. Okay. And again, there's a case D that says no such T prime exists, T double prime. Okay. So let me jump again, as before, the first case is the interesting one. Let me just say quickly that in case D, we're ready to set alpha R plus 1 to just be alpha prime. And I'm going to argue that this is okay. And in fact, I'm going to set R prime to just be R sub R. Let me not argue why this is okay. Let's instead look at the interesting case where we have to do work. In case C, we fix a minimal T double prime and a corresponding beta double prime. Okay, and again, by lemma 15, we know that beta double prime without loss of generality is size of alpha prime plus S minus R. Right? Because we have the space bound, we have this many non-zeros. Then we know that so gamma is like any beta double prime that we found, and then this lemma says that without loss of generality, it has additional size of both S minus R. Okay. By condition 2 plus lemma 13. Beta double prime forces M sub T double prime. Because again, we're at the space bound, so we actually have to have equality, and we know that already alpha guaranteed this many zeros. Sorry, something that I said was wrong. No. We're not at the space bound. R is not S, but we know by this case, we found a T double prime such that this equality holds. Okay, so this equality holds. How do we know that this assignment guarantees R zeros? Well, this we know from condition 2. So lemma 13 then says that beta double prime actually satisfies the condition for forcing empty. Now I claim that actually this means that it forces T double prime to false. Why? Well, we're over here, right? Suppose that it actually forces this configuration to true, then I would have chosen T prime to be this. Because T prime was basically the same, plus I pick this maximal plus I want to force the configuration to true. So I know beta prime forces the configuration. If it would force it to true, then I would immediately shift t prime over here. But t double prime is larger, right? Because L prime is in fact t prime plus 1. So I know that it can't be that t prime and t double prime are the same. And therefore, by maximality of t prime, what the value it's forced to cannot be true, so it has to be false. Are you with me? Excellent. And now, that means that in fact, we know that t double prime is then actually larger than L prime also. Because note that alpha prime was actually forcing t prime at time t plus 1, it was forcing to true. And beta double prime is extending alpha prime. Okay, so now what do we have here? Maybe it's time for to expand our picture a little bit. Basically here is t double prime. And I claim that beta double prime forces mt double prime to false. And again, how much did we grow? By s minus r, a third factor. You know, we have like 4, we can do 4 times s minus r. We've done 3 times now, so we're clearly almost done. Unless if I get lost in my notes, which is going to be a very bad thing. Okay. Now use lemma 14 to get alpha double prime extending beta double prime. Alpha double prime should obviously still live inside the family. Alpha double prime is less than beta double prime plus, you guessed it, s minus r, which is now, we see that, so alpha double prime, just let's write it down, it has size, I've now found an alpha double prime of size actually at most 4 times s minus r plus alpha r. And what more properties should it have according to lemma 14? So this, we have the space bound, alpha guarantees r non-zeros. Then there exists a beta, which is our alpha double prime, that forces m. So again, I'm using the fact that now I'm hopping over here to m t double prime minus 1, right? So I'm extending by s minus r more, and now I'm going to force this configuration to some truth value. And lemma 14 says that I can do this in such a way that alpha prime forces m t double prime minus 1. So now again, lemma 11, recall that we've done our calculations, we're always below this bound. So now lemma 11 says that alpha double prime then forces m t double prime minus 1 to false. Now we're ready, because I am going to set, so basically this value now is going to be LR plus 1, T prime plus 1. T double prime minus 1 is going to be RR plus 1. And one thing I have left to argue, but you can already see from this picture that we sort of picked the last time when I was forcing to true and I was down on the minimal number of zeros, and I scanned from the other side and picked the next time before that I was down on R. Okay, so I know that there's nothing that hits exactly R in between these two, and then I took one step in both directions. So you see that if I look at this interval now, I should have one more zero. Proof by picture. Okay. So I claim that we're done. So again, LR plus 1 is L prime. R plus 1 is R prime, which is equal to T double prime minus 1. Alpha R plus 1, I'm going to set this to be alpha double prime. And now let's check conditions. Clearly, we're forcing this configuration to true, we're forcing this configuration to false. Are you with me? Like, I think this is okay. Also, I mean, how much did we grow we grew the assignment by this much. Okay. So what about condition 2? So let's take this nice and slow. We know that alpha R, which we started with, guarantees R non-zeros in the interval LR/RR. By the choice of LR plus 1 and RR plus 1, we know just by looking at the definition, for all gamma in A, such that gamma are extending alpha double prime, which is alpha R plus 1, and for all T in L R plus 1 R R plus 1, we know that the number of non-zeros of such an MT with respect to such a gamma is not R. Why? Well, because LR we picked to be the largest value for which we were fixing the configuration to true, or forcing the configuration to true, and then we scanned, then we moved one step, and then we just scanned from the other side and picked the earliest point where I had guaranteed only R. So if there would be a gamma somewhere in between these two, where the number of zeros were R, I would have shifted either T prime or T double prime. Are you with me? Okay, so I know just because of the maximality of T prime and the minimality of T double prime, there is no gamma satisfying this for T inside this interval. But I am guaranteeing R non-zeros. So if I am guaranteeing R non-zeros, but I never hit value R, that is the same thing as saying that I'm guaranteeing strictly more than R non-zeros. In particular, at least R plus 1. Done. Okay. so this is a good time to take a break, and then when we come back, I do want to try to do some size degree trade-offs. Let's see how much we can do. Before we take a break, I asked you to help me with questions about the trivialities. You didn't really do that, except you did point out lots of embarrassing typos, and I'm grateful for that. Any questions before? Because now, like, what I'm trying to, I'm arguing that nothing is really happening here. Like, it's all this, you have this forcing notion, and then this other magic notion that you realize is somehow this notion of guaranteeing non-zeros. What are these guaranteeing non-zeros? These could be, for instance, these high-degree monomials that we failed to set before because we wanted to set them to 1, but we didn't have enough budget to sort of set all of the variables in them to 1. And then somehow this forcing relation says, well, if it's a high-degree thing, but in your strategy it sort of never gets set to 0, then assume it's being fixed to 1, and you don't even have to pay for it. And then you just do this magic argument that the only thing where we're losing, like every time we're shrinking this interval, we're paying a factor s. And we need to shrink, and every time we're shrinking the interval, we're increasing the non-zero guarantee by 1. But we have to guarantee at least s non-zeros in order to get these lemmas to play. And that's why I'm going to shrink s times, increase the count by 1, by paying s, so that's where I pick up the s squared. Somewhere here, it's reasonable to believe that there's slack, that somehow we should be able to do something better. Or at least, like, if you force me to guess, it's not this time. This argument doesn't look tight to me. But of course, we have no idea. But it doesn't taste like it's tight. Questions about this before we take a break? Or should you just philosophize over it during the break? Okay, let's philosophize for 10 minutes, and then we'll be back. Okay, so we're switching gears completely. We're switching from polynomial calculus to Nullstellensatz. What is Nullstellensatz? Again, we have a bunch of polynomials, pi. We're interested in 0-1 solutions. And therefore, we're looking at an assignment that zeroes out all polynomials, and that also respects that x squared minus x is 0 for all variables x j. How do we make this into a refutation system for CNF formulas? Well, if we have a clause with positive literals x and negative literals not y, then I can just turn it into a polynomial, which is the product of 1 minus x for all the positive x's times y for all the negative y's. Note that today I'm switching. I already warned you before. Today it's convenient for me to think of 1 as true and 0 as false. So this is going to be my translation today. And then the refutation, the proof that there is no assignment satisfying all these polynomials corresponding to the clauses, or in general, p could be any polynomials, is a combination of the pi's with other polynomials qi's, such that when I sum up qi times pi plus some other polynomials rj times xj squared minus xj, and take cancellations and everything cancels, then syntactically I get 1. I don't get a function that evaluates to 1 like I syntactically get 1. And the size of this refutation is just expand out every one of these polynomial products individually, look at the number of monomials, the total number of monomials counted with repetitions, that size, and the degree of the refutation is the largest total degree of any monomial. And it's natural, since we've been talking about trade-offs before, you could ask whether you can minimize both of these measures simultaneously. You could also ask this for polynomial calculus. We won't have time to talk about polynomial calculus now because I did the monomial space law one too slowly. But note that for polynomial calculus, we actually know that if you have a good enough size upper bound, then you can convert that to a good enough degree upper bound. You can take a small size polynomial calculus refutation and turn it into a somewhat small degree polynomial calculus refutation. When you do that, however, size blows up terribly. It's natural to ask in general whether there are size degree trade-offs or whether you can optimize both measures simultaneously. For Nullstellensatz, there is no such connection. For Nullstellensatz, just because the size is small, the degree can still be essentially maximal. But also for Nullstellensatz, it's still reasonable to ask because many, if you're actually using Nullstellensatz algorithmically to prove lower bounds, typically you'll try to minimize the degree. And it's natural to ask, like, can you minimize the degree without taking a penalty in the size, or could it be that there are trade-offs? Okay, so this is the question today. The answer is, like the spoiler alert, because we're low on time, yes, there are trade-offs. What are these formulas? Pebbling formulas, so let's recall what they are. G is a directed acyclic graph with a single sink, which will always be Z. I will associate the variable x sub v for every vertex v, except sometimes I might be lazy and I might overload v for both the vertex and the variable related to the vertex when it's clear from context. One convenient piece of notation for monomials will be if u is a subset of vertices, capital U, I might just write x sub capital U. And this is just the product of the xv's for all vertices v and u. You're happy with this? So in particular, and if I'm then overloading x, v, and v, that means that capital U, I could also overload it to be like a product of vertex variables, except I don't think I will do that. Okay? And let's recall what pebbling formulas are in algebraic notation. So skipping straight to algebraic notation, pebbling formulas for a graph such as this pyramid graph over here says that all the sources, that is, vertices without incoming edges, they're true, they're 1. And this is forced by, you have to satisfy 1 minus xp, 1 minus xq, 1 minus xr. So you have to assign all of these variables to 1. The pebbling axioms then say that if both of my predecessors are true, then I am true. So here we say that if xp is true and xq is true, that forces xu also to true, because otherwise 1 minus xu will not be 0, and then this polynomial will not be 0. Okay. Similarly, if x, q, and xr are both 1, this forces xv to 1. And then if xu and xv are both 1, then this axiom, pebbling axiom here, xu times xv times 1 minus xz, forces the sink z to 1. However, for the sink, I have a special sink axiom that says that the sink has to be 0. Just to introduce a piece of notation, it will be convenient for me to write all of these axioms as AV, and note that they are really x pred v times 1 minus xv. Because for sources, this is just the empty set, which corresponds to the multiplicative constant 1. And then I'll have a special notation for this final sink axiom. I'll just call it async. Okay? So these source axioms and pebbling axioms, I can just fold them into a single notation. Are you happy with this? Okay, so my claim now is that, and in fact, okay, so now it turns out that there are always small Nullstellensatz refutations of these formulas, of these algebraic principles. However, the degree is captured by the pebbling graphs. Except we have to fiddle a little bit with the pebbling game. So let me tell you what game we're going to look at. We're going to look at reversible pebbling. Reversible pebbling is basically the black pebble game we had before, except that it should be valid if you run it also in reverse. So what does this mean? Well, the nicest definition of a reversible pebbling is then to say the following, that we start with a pebbling configuration is just a subset of vertices, namely the vertices that have pebbles on them. We start and end with empty configurations. Somewhere during the pebbling, we should touch the sink with a pebble. And then, as before, P sub t follows from P sub t minus 1 by pebble placement, and this is just as before. So pebbling placement on V is, we're adding a pebble on V, so PT is PT minus 1 union V, assuming that all the predecessors are already there. You can only pebble a vertex if the predecessors are there. So this is what we've had all along. Now the second move is removal, and remember before you could always remove a black pebble. It wasn't a problem. But now we want this to be valid when we run the pebbling in reverse, so therefore we need that also for removal the predecessors should be on the graph. Okay? So, and now with this modification we can still define pebbling time, and pebbling space is obviously the maximum size of a configuration here, right? So one convenient observation is in fact that we could have, the definition could equally well be this, that a reversible pebbling is a sequence of configurations such that we start with emptiness, Z is contained in P tau, and the time of the pebbling is 2 times tau. Why is this? Well, sort of, if I'm giving you a reversible pebbling, I only have to tell you the pebbling up until the first time you touch Z. Because if you did an optimal pebbling, at this point you will just reverse and run the pebbling back. Because suppose you did something smarter on the other side, well, then you would run that pebbling in reverse instead of your pebbling here. Am I making sense? So like without loss of generality, you just run a pebbling strategy up until the time you hit S, and then you just reverse. This is like without complete loss of generality, because if that is not optimal, then look at an optimal strategy and pick the optimal half of it. Am I making sense? So actually we're going to look at reversible pebblings like this from now. Now the theorem that we're claiming, I don't think we need Nullstellensatz any longer. I hope we remember what this is. So the theorem is assuming, again, a single sync tag with a single sync set, etc., etc. F is any, capital F now, or fat style F is any field. So the theorem, which is by the Rezende, Meir, myself, and Robert Robert, is the following. There is a reversible pebbling P of the graph G with time of the pebbling is T, space of the pebbling is, actually let me not put equality here, less equal T, and space is less equal S, if and only if there exists a Nullstellensatz refutation phi of the pebbling formula for G in the algebraic notation, such that the size of pi is at most t plus 1, and the degree of pi is at most less. So I think this is, the reason to do this is this is not going to be hard, so hopefully we'll have time to do it. And notice that this is extremely tight. I mean, there are no asymptotic notation anywhere, there's no constant slack even. Like, you can do this in both directions. And it holds regardless of the field. So, which means that if you care about optimal Nullstellensatz refutations of pebbling contradictions, you couldn't care less about the field, because if you had a good refutation in one field, like take it, turn it into a reversible pebbling strategy, and then translate that reversible pebbling strategy to a refutation in your favorite field. And you'll just get something better. And in the way we're going to prove it is just by taking a reversible pebbling with whatever these measures are, and we'll get a Nullstellensatz refutation that have the same bounds, and then we'll do it in the other direction. Okay, is the statement making sense? So we're now going to take this view. So suppose we have a pebbling like this, P0, P1, P2, P3, P tau minus 1, P tau. What am I going to do? I am just going to derive for every pebbling move, I'm going to derive the monomial x p. Here I derive x p0 minus x p1 plus x p1 minus x p2 plus x p2 minus x p3 plus, let's see, what do we get? X p tau minus 2 minus x p tau minus 1 plus x p tau minus 1 minus x p tau. We'll talk about how to do this. Okay? Suppose I can do this. What do we have? Well, firstly, there's a nicer name for this. What is this? What is xp0? It's 1. Right? P0 is emptiness. What is this for an empty configuration? It's a 1. Okay, so I have a 1 here. That's a promising start. What happens, and then you notice that xp1 cancels, xp2 cancels, xp3 cancels also. All of these guys cancel. This guy doesn't cancel. But we're already pretty close to a Nordström refutation. How do we get rid of this guy? Well, note that Z is contained in p tau. So certainly I can just take the rest of the guys that are in here, multiply by this axiom and subtract. Okay, suppose I can pull this off, what will I get? Well, for every, so here I will need to do an extra plus xz times, let's write this down, xp tau minus z, right? How many monomials do we have here? Well, for tau, we're picking up 2 for every step. So we have like 2 tau plus 1 monomials. Tau is half the time, right? So 2 times half the time plus 1 is time plus 1. What's the degree of this? Well, the space, right? So if we can do this, then we're done. Note, interestingly, that we didn't use any Boolean axioms. We only used the input axiom. So this means without loss of generality, suppose I have a super clever Nullstellensatz refutation that actually uses Boolean axioms, then supposing that I can do this translation that we did not do yet, I can always get a smaller refutation without using Boolean axioms, without loss of drowning, if this theorem is true. We're doing this downwards direction now. Okay. So all I need to do now is to argue how to derive x p t minus 1 minus x p t. Okay? So note that it always holds that the intersection of pt minus 1 and pt is the same as their union minus v. And this is because we're reversible now. Whenever something happens with v, it's because, I mean, we're adding or removing v. And we also know that the predecessors of whatever happens is in both pt minus 1 and pt. This is not true for a general pebbling as we had before, but for reversible pebblings it's true. Okay? So let me set RT to be pt minus 1 intersection pt, except I'll remove the predecessors of v. Okay. And now I just have two cases. For pebble placement, I claim that x pt minus 1 minus x pt, that's just going to be x RT times the axiom for v. And for removal, I just do minus x RT times AV. Done. Note we're using no Boolean axioms and we're multilinear. I was actually planning to, if we could spend 2 more minutes on it. Like basically this is it. So one thing we could do, it will take us 2 minutes. It's just let's see how this actually works. And let's do this because we're going to use it in the other direction. So let's actually do a pebbling. Okay? Let me start by pebbling P. It's not going to be an optimal pebbling, but I just want to illustrate it. Then our rule, okay, so maybe let me write down what did our rule say? We should do x RT times the pebbling axiom for V. And we should do plus minus, plus for placement, minus for removal. Right? This is our rule. Okay. RV and RT was again equal to PT minus, let's play safe, let's remove both V and the predecessors of V. That should be an okay definition. Oops, I don't need the extra. I need it. I want parenthesis V union predecessors of V. Okay. So for the first pebbling move, RT is nothing. So I just get 1 times the pebbling axiom. Now actually let me start being lazy. Okay, so this is move 1. Move 2, now RT is P, and I multiply that by 1 minus Q. Now I pebble U. Then actually you realize that RT is again nothing. So now I actually just want plus PQ times 1 minus U. Now let me remove P. Okay, then I want to take a negation. And now I think I want to do QU times 1 minus P. This is, at this point in time, is when I'm going to start to screw up, so you'll have to help me. Now I pebble R. I think I want to do again QU times 1 minus R. Now I pebble V. Now I think I want to do U times the axiom, which is QR times 1 minus U, 1 minus V, sorry, 1 minus V, 1 minus V. Now let me remove Q, just to make life a bit more interesting. Now I have a minus. And now I actually have RUV times 1 minus Q, right? And now I pebble Z. Okay, so then I should have R times the pebbling axiom for Z, which will be UV times 1 minus Z. And now the claim is I'm going to have what will be left. What should be left is this one. I will be left with this also, but this is easy to remove. This I'm just going to multiply. So basically here it's clear what I'm going to do now is I'm going to do RUV times Z. And now we just need to take a deep breath and say that this and this is going to cancel. PQ and PQ, these two are going to cancel. Here I have PQU, here I have PQU, so these two are going to cancel. I have minus QU plus QU, these two guys are going to cancel. RUQ, RUQ, these guys are going to cancel. I have RQUV, RQUV, these guys are going to cancel. Sorry, these guys are going to cancel. And these guys are going to cancel. And then these guys are going to cancel. Kind of, sort of. Okay, this is actually the proof. You're buying this? Okay, excellent. Then we're actually going a bit faster than I thought. Excellent. So now we only need to do the other direction. And once, okay, what's the point with it? Okay, so this I forgot to say. So, and where does this even come from? I could say, okay, a short interlude. Nullstellensatz. Then there are some notes here in the lecture notes that I won't really have time to talk about. But basically, Nullstellensatz, there was substantial work on this around the turn of the millennium when it was defined, and then several papers proving lower bounds for our favorites, pebbling formulas, pigeonhole principle formulas. In particular, it will follow from this. Yeah, so I forgot to say that this will show pebbling formulas are always, this already tells you that there will be a separation, right? Because we do have pebbling formulas. Any pebbling formula is pebblable in linear time. So that tells you that there is a very small Nullstellensatz refutation. However, there are graphs for where already the standard pebbling price is n over log n asymptotically. Clearly, the reversible pebbling price cannot be better, right? In fact, it's also n over log n. This is not obvious. But so that means that already this connection tells you that you can have degree n over log n, where n is the number of variables and also the number of axioms, in constant degree, degree 3, without having any lower bound on size, right? So these are the kind of results that, and some, this was actually first noticed by Boris Schopenheim, Clegg, Impalazzo, and Tifassi, I think, and then was sharpened a little bit by us. They didn't have quite this. And then people moved on to stronger algebraic proof systems like polynomial calculus for almost 20 years. And then I think it's fair to say that Robert, sort of together with Tony and Pitassi, revived the interest in Nullstellensatz, because it turns out that if you have strong enough Nullstellensatz lower bounds, then you can lift them to much stronger proof systems. So one thing that we will see briefly later in the course is if you have good enough Nullstellensatz lower bounds, this actually tells you highly non-trivial things about cutting planes. It's not obvious at all. Okay, we'll see this. So then, starting in 2016, led by Robert and Tony, there was a lot of renewed interest in Nullstellensatz. And then, as a byproduct of this interest, and as a byproduct of one of the other papers that we'll talk about, namely using Nullstellensatz to understand the power of coefficient sizes in cutting planes, this just sort of came up. This very, very cute thing that we will see today, which I thought I would share with you because I think it's cute, and this connection will be handy for us later. That concludes the detour. Now, what do I need to question so far while I'm thinking about what to say next? Or are we happy? Let's go in the other direction. So now we want to convert Nullstellensatz refutation. We already converted a reversible pebbling to a Nullstellensatz refutation with the same parameters, except that we picked up one extra monomial to zero out the sink. So now we want to go in the other direction to convert a Nullstellensatz refutation to a reversible pebbling. Okay, now I'm going to cheat. I'm going to do this over GF2, just because it saves us 5 minutes. Okay, if you understand the GF2 idea, and you think about it, we can talk about briefly. It's not hard to fix it. It's very clean for GF2. You'll see. This in particular means that I can write a plus here. Let me just do that for simplicity. Okay, you're fine with this? Let's do it. Okay, let's look at this derivation again. I'm actually going to do it by example. So given pi, we're going to build a graph. H of pi. The vertices are the monomials. Okay, so in particular, what do we have? We have the empty set is a monomial, or like 1. We identify them. What more monomials did we have here? We had the monomials P. We had the monomial PQ. Then we had the monomial PQU. And then we had the monomial QU, yes? QU, and then we had RQU. And then we had QRUV. QRUV. And then we had the RUV, and then we reached RUVZ, and then we ended. Okay. Okay, we're gonna do edges between. So the Nullstellensatz refutation, let me write out pi. Okay, I'm going to do it over GF2. I forgot to say one more thing. Let's do it in a multilinear setting. I will multilinearize. So I get rid of the Boolean axioms. This can only make the strong, like I have any Nullstellensatz refutation in some size. I multilinearize it. This can only decrease the size of the degree. And then I will do the translation for the multilinear version. Okay. So we're multilinear, which means that pi will look like QV/AV plus Q_ASync equals 1. Okay, and now I'm going to have an edge I'm going to write this somewhere. Maybe down here. Okay. For every xv in qv, so for every monomial x capital W in qv, where's qv? These guys. Okay. What will this monomial in qv, what monomials will it actually give rise to? Well, one will, you realize that one of the monomials will be W union pred V, and the other monomial will be W union pred V union V. So I'll just add that edge. Okay, what do I do with this guy? Nothing. Let's look at our example derivation again. So first we had here xv was 1. So this gives us this edge. Here we get this edge. Here we get this edge. Here we get this edge. And then we get this edge. I think. No, we don't. Hang on. We can't. We get this edge. Then we get this edge. And we get this edge. And we get this edge. Yes, sorry. We always have a, like we always grow. I mean, the set size difference is always exactly 1. Okay. This is our graph. And I'm now going to use this to build a pebbling. I claim we're done now. Okay. Observations. My first observation that if you look at the degree of 0, it has to be odd. Why? Well, because every edge corresponds to one appearance in the proof. And we know that 1 appears an odd number of times because it doesn't cancel. Okay? For the same reason, we know that if it's not the case that the sink is in U, and if U is not empty, then I claim that the degree of U is even. Because all of these guys appear an even number of times. They cancel. This guy also cancels. We don't see that, but that's because we're ignoring this guy. But clearly, throwing out this guy, all of these monomials contain Z. So everything that not contains Z has to cancel, and these edges are faithfully counting occurrences. Okay, and here's the punchline, or 2 punchlines now. Note also that by construction, every edge is a valid pebbling move in both directions. Right? going between this configuration and this configuration in either direction is always fine. This is a placement, this is a removal, and there are no other rules. Okay, fantastic. So we do know that there is a component in the graph which contains an odd degree vertex. And we know that all other vertices that don't contain Z have even degree. So it follows from this that there exists a path from 0 to some U containing Z in this graph. Right? I mean, because the sum of the vertex degrees in a connected component in the graph, unless you believed Satin formulas, which you shouldn't, you know, I start here with an odd degree vertex, and then I'm walking across even degree vertices. This can only end when I hit an odd degree vertex. And indeed, this is kind of a boring, here there's only one choice, but basically I'm saying that this, then 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 this has to be a valid pattern. And in any, again, this is, I'm doing this by example because, well, because we have limited time. But I'm claiming that I'm making it believable enough that this will actually work in full generality in GF2. Okay? And let's see what we get. What is the space of this pebbling? Well, obviously at most a degree. I mean, because these are the monomials. We have a vertex for every monomial in the refutation, and the space never goes above this. So clearly, the pebbling space is upper bounded by the degree. What is the time? Well, okay, so I claim let's see what we have. Space is like blindingly, obviously upper bounded by degree. The pebbling time is, we're counting the time, note that we're counting the time to get to Z, which is half of the time. So time is at most 2 times, you know, the time to get to Z, which is at most 2 times the number of edges. And now you see that I claim that if you look at what is the number of edges, well, again, we're throwing out this. So we actually get S of pi. We're removing at least one monomial. I mean, this contributes at least one monomial. And every edge is actually contributing So note that every edge is actually mentioning 2 monomials. So the number of edges is the size divided by 2. Except I removed this guy. At least. There could be more, right? But there's at least one monomial there. So there's at least this one. And then the edges is half of the size. Half of every edge sort of contributes 2 monomials. So that's why I divide by 2. But then I should multiply by 2 because I only counted until when I reached Z. So then I claim we're done. Okay. What if I want to get this for arbitrary fields? Well, then you need to have weights on the edges. And the weights are basically going to be the different coefficients for the monomials when they appear. And now you're going to do some kind of parity argument except modulo the characteristic of the field. And so you can define sort of the total weight of all the vertices, and that's going to be the weight of a vertex is kind of summing up all the weight of the edges. And since you move between odd and even-sized vertex sets, you're going to argue a little bit with plus. There's going to be a plus-minus adjustment depending on whether the set size is odd or even. But then you're going to have, again, the same argument that this has, like modulo the field characteristic, this vertex has weight 1. Modulo the field characteristic, all of these vertices will have weight 0. You will observe that if you have odd-numbered and even-numbered set sizes, you will only have edges going between even and odd. So this graph is in fact bipartite. So, and now you just sum up the weights on both sides and you realize that I have a bipartite graph where on the left side, everything is 0 mod the characteristic except this guy. And then on the other side, all of these vertices will also be 0 mod the characteristic. And the only guys that could not be 0 mod the characteristics are the guys that contain Z. So again, you have a bipartite graph where unless you could walk back and forth in the bipartite graph from 1 to some configuration containing Z, then you have a connected component where the vertex, where sort of the sum of all the edge weights on the left and the sum of all the edge weights on the right won't match up, and that doesn't make sense. Right? Summing the edge weights in 2 different ways, the same edge weights, like, should give you the same answer. They're just going to be basically the same argument. Okay, so once we have this, now you can use reversible pebbling time space trade-offs to get Nullstellensatz size degree trade-offs. So this is the second part of what we do in our paper. And there it actually, I don't think, okay, so maybe I'll state one example theorem just to show you what the results might look like. But I should say that this is actually one area where this could potentially be improved, because there is not too much work done on reversible pebbling time space trade-offs. So basically what we did is we take the strongest standard pebbling trade-offs that we know. The lower bounds obviously still hold, and then you have the problem that the upper bounds actually don't hold, and then we have to work and see, can we reversibly, people have been working on how to simulate non-reversible pebblings reversibly as efficiently as possible, and we sort of recycle those types of results and try to do our best. But we don't get, recall that, I mean, this result is as tight as can be, this is exact, right? But recall that when we had the length clause-based trade-offs for pebbling formulas with substitutions, those were asymptotically tight. We inherited exactly the parameters of the pebbling trade-offs. And when we had asymptotically tight matching results for black and black-white pebbling, that meant that we actually got asymptotically tight results for resolution. We're not in this situation here. Like we don't have tight upper and lower bounds in the trade-offs because we don't understand reversible pebbling that well. So, but basically you could get something, okay, what are results that you could get? For instance, there are formulas Fn with a linear number of clauses and variables where the degree in Nullstellensatz of refuting Fn is, say, at most some d1, which is big O of 6th root of n, log n. There will be a lot of logs. The logs you typically pick up when you simulate a non-reversible pebbling reversibly. And then you say there exists refutations pi such that the size of pi is essentially n to the 1 plus epsilon. You can pick epsilon arbitrarily small. So these are very small, but the degree is now d1 times another 6th root of n. So meaning big O of 3rd root of n log n. So you blow up the space by a square. This is the degree efficient, this is the size efficient thing. And then you say that if the degree of pi is less than k times d2 over log n for some k, there exists a k, and then for any epsilon there exists a k such that this holds. And this again, this will be big O of 3rd root of n. So basically we know that you can get down to 6th root of n essentially. We know that in small size you can get 3rd root of n. As soon as you want to go below 3rd root of n, the size will actually be 6th root of n factorial, so exponential. Okay. What would be nice to have are tighter trade-offs, in particular getting rid of all these logs and stuff. Like there are really tight pebbling trade-offs for black pebbling and for black-white pebbling, for reversible pebbling not so much. Any such improved results would immediately get better Nullstellensatz trade-offs. In particular, one kind of intriguing question is, for black pebbling, we know that there are graphs which are pebbleable in space S and which have linear time pebbling in space S plus 1. But when you go from space S plus 1 to space S, then the pebbling time blows up from linear to exponential. There are such results, like extremely sharp trade-offs. We don't have this for resolution length versus closed space, because remember there we only have asymptotic things. Such additive constants just get lost in the analysis. Okay, but here we would actually be able to pick up such additive constants. So if you would give me a reversible pebbling trade-off where you can do space S, but anything below space S plus 1 blows up time exponentially, that would give the same kind of extremely sharp Nullstellensatz trade-off. Is this possible? Could this possibly be true or not? We don't know. Okay. But I think it's an interesting question. The third thing, though, which is the most important thing, is note that we had no dual variables today. We did Nullstellensatz without dual variables. We only had x, y, z. There were no x bars around. Okay. What happens if you allow x bar and y bar? This crashes. This is really hard. I mean, we know that the degree doesn't care whether you have dual variables or not. So the fact that in particular, it follows from this that Nullstellensatz degree for pebbling formulas is exactly characterized by reversible pebbling price, right? This is what this says. That reversible pebbling price and Nullstellensatz degree are exactly the same. No slack, no additive, no nothing. Okay? And this still holds in the dual setting because degree doesn't care. But what we lose is this correspondence between pebbling time and refutation size. Because when you have dual variables, potentially you can sort of compact your monomials more efficiently. And I think we actually have, I don't remember, like we were working on this, and I think we convinced ourselves that actually this just cannot, this type relation is false, because that you can show that Nullstellensatz with dual variables can do better than this. And at some point we believed, I think, that we understood it, but then it somehow, I don't know. Maybe it fell apart, or maybe we didn't write it up quickly enough for it. So I think this is a nice problem. Like, can you get something like this for Nullstellensatz with dual variables, or any size degree trade-off for Nullstellensatz with dual variables? Because here we're extremely crucially using the fact that we don't have dual variables. Yeah. So I'm sorry, I know I'm pushing late today. I want to just summarize, because I think now we're leaving space complexity behind. I think we're now planning to move on to cutting planes. So I just want to summarize. The reason we did these last lectures before and after Christmas was because of the many nice open problems, which I think would be good problems to work on. I already talked a little bit about Nordström. Let's also recall what problems we had for space. So one question is it possible for resolution to have refutation space of a formula? So say we have a k-CNF formula f, let's say that it's over n variables, just for concreteness. Is it possible that the clause space would be linear and the refutation length would be n log n? So note that we have clause space lower bounds n over log n and length upper bounds n. Can we push the clause space all the way to linear while still keeping length small? Or is it maybe, could it be the case that, well, actually linear clause space implies that the formula is super hard? Note that we have this for polynomial calculus. But for polynomial calculus, somewhat annoyingly, this lower bound is degree dependent. Okay, so this is another way, another open question. Can we do this for polynomial calculus, but independently of the characteristic? Second question is, I already said it would be really nice to understand if it is the case. Can we find a family of formulas where the monomial space is asymptotically smaller than the resolution space? Like everything we know, clause space and monomial space coincide asymptotically. We have no separation. Although we know with respect to degree versus width, we have extremely strong separations. Size, we also have exponential separations. Space, we don't know. Another somewhat related question is whether you could separate monomial space over different fields. I don't know. I haven't thought about this at all, but again, note that it's a reasonable question. Right? But for instance, Thapen formulas will not work because although Thapen formulas are easy in GF2, we do know that they can have linear space lower bounds. So we don't expect this to be an example for this. The obvious question, given what we've done today, is can we remove the square root from the claim that the monomial space of refuting a CNF formula F is at least asymptotically the square root of the resolution refutation width? This is what we did before the break today. Can we get rid of this square? Or could it somehow be tight? Or could it be that, remember, we actually didn't prove the lower bound for PCR. We proved the lower bound for functional monomial calculus. Maybe this is for some weird reason tight for functional monomial calculus, but not for PCR. We don't really know. I think my guess would be that even for functional monomial calculus, somehow the truth is there is no square root, but what do I know? Note also that this only worked for CNF formulas, right? You know, we were heavily using this defendant strategy all the time. So actually, what if we look at, is it true in general for, say, constant degree polynomials? Is it true that the monomial space of refuting a set of polynomials is, you know, big O of big omega of the degree of refuting this set of monomials? Maybe to some power delta for, you know, some delta greater equals 0. Delta half is what we could shoot for now, or, you know, delta equals 1, or delta something, or even big omega of 1 here. But note that the result we did today very heavily used the combinatorial characterization of resolution width. We don't have such a nice characterization of polynomial calculus degree, except we do have, I mean, we did play around with these pseudo reduction operators and so on. You know, could you do something with them to get some kind of general lower bound that works also for non-CNFs? And just two more questions. So, could we get tight monomial space lower bounds for the usual suspect? I mean, so we know that we can do it for pigeonhole principle. We can't do it for the functional pigeonhole principle, and even less for the onto functional pigeonhole principle. Can we do it for any setting formulas on expanders? Again, note that the bizarre situation we have now, if I give you a 3 regular expander graph, and then I make it 6 regular by adding a copy of every edge, turning it into a really lousy 6 regular expander, but it is an expander, then we know optimal linear monomial space lower bounds. Okay? But if I give you just a 6 regular expander, then all I can prove is the square root lower bound. Is that really, is that the truth? It's hard to believe. Also, ordering principle formulas. You recall that we talked about partial ordering principles, linear ordering principles. I think we talked briefly about dense linear ordering principles. We don't have, what do we have for these? Well, we have the space lower bounds that follow from resolution with lower bounds and the square root loss. Right? This is like, for all of these, we have lower bounds with the square root loss that we get from what we did today. But can we get rid of this and get tight linear lower bounds? And my favorite, for which Galesi, Kołodziejczyk, and Thapen doesn't give us anything, and this I think, you know, I can't help thinking that this should be doable. What about pebbling formulas? Pebbling formulas with XOR substitution, majority of 3 variable substitution, indexing gadget. Pick your favorite gadget, ideally constant size, but at this point I'd even buy, like, you know, non-constant gadget size. Prove a monomial space lower bound scaling with the black-white pebbling price. Would be really nice. And finally, final question, and then we're ready to take questions and end this lecture. Can we find some formulas where the total space in PCR of refuting them is at least, you know, is the number of variables squared? Okay. Note that this is what we got to yesterday for total space in resolution. We should specify this, something we did not talk about. Well, if I wanted, oh, sorry, or oops. I mean, you could ask for this for f or for p or anything. You should ask for these formulas to be polynomial sized though, because in the ABRW paper, they actually have a total space lower bound in PCR that scales quadratically in the number of variables, but they are for exponentially large formulas, the so-called complete tree formulas. The complete tree formula over n variables is you add 2 to the n clauses of with n, namely one clause for every possible truth value assignment, and then you add them all together. So that's an exponentially large formula, but only over n variables. And ABRW proves for this formula that actually the total space, even in polynomial calculus, is the number of variables squared. But of course, we would like to get this result for some polynomial sized formula. I think all of these, not all of these problems are maybe equally exciting, but many of them are really, really good. I mean, I think based on what we did today, like I really think it would be worth to think seriously about whether Galesi, Kołodziejczyk, Thapen could be improved. I really wonder about the pebbling formula space complexity with respect to polynomial calculus. Also, functional pigeonhole principle and side. It's just weird that we cannot prove monomial space lower bounds for these. Total space lower bounds for PCR is a great question. I didn't put it here, but I said it before. Nullstellensatz trade-offs. Maybe put it here. Nullstellensatz size degree trade-offs when we also have dual variables. Okay. So I think there are. And the characteristic, this kind of separation by characteristic independent for polynomial calculus space. Separating monomial space and closed space. Can they really be the same asymptotically? Yeah, I guess, trying to motivate you or the people in Copenhagen or whoever will be listening to this on YouTube that these are questions that seem well worth looking into. I don't think that they are. It's not like they're open because people have been studying them for years and years necessarily. I think. I don't know, but at least I think it's perfectly conceivable that just sitting down and thinking hard about these problems for a while and maybe getting the right idea that that's significant progress. Okay, it's well past time to start talking. Any questions before we call it a day? Okay, good. Thanks so much for today.